Hey everyone, thanks for coming. So like Tim just said, my name's Pat. I am a software engineer on the stream infrastructure team at Temporal, at Stripe, and I'm here today to talk to you about mastering Kafka at scale, unleashing the power of Temporal at Stripe. So just to give a little bit of an outline of what I'm going to discuss in this talk, first I'm going to give you a brief overview of what the streaming infrastructure setup is at Stripe to motivate the reason for why we would want to use Temporal to manage all of our clusters. Next, I'll introduce what the Kafka Control Plane is, which is this piece of software that we've developed at Stripe to manage all of our Kafka clusters. I'll then take you through some of our workflows, which I believe and my team believes are really good examples and motivating examples for when you'd want to use Temporal. These include the archive monitor workflow, which we use for making sure that all of our data from our Kafka topics is stored safely in S3 for retention. The replace broker workflow, which we use for replacing brokers throughout all of our clusters at Stripe. And also, I'll briefly touch on the Kafka Planner workflow, which is a workflow that we use for ensuring the integrity of our system. I'll then talk to you about a fairly novel piece of software that we wrote called the safety barrier, which we use for ensuring that all of our workflows are running safely and properly. And then I'll go into some key takeaways to discuss some of the things that we learned, as well as maybe some of the poor design decisions that we made along the way. So at Stripe, we have three major components that comprise our infrastructure setup. We have our Kafka clusters. We have approximately 50 of these clusters that span across three environments. These clusters are range in size. Our largest one has about 90 brokers, and some of our other clusters have about 45. Our smaller ones have only maybe 2 or 3 brokers, depending on the environment that they're in. But yeah, we manage a lot of, since we set up everything ourselves, we have a lot of instances and brokers that we have to manage. Since we are a payment processing company, we have a layer on top of our clusters that we call K-proxy. This is pretty much just a load balancing, event routing API that we use to ensure high availability, because as you configure, we don't want our service going down, like we're payments. So the next thing that we have something called the Kafka archiver. What this is whenever a user writes an event to one of our Kafka clusters, we take this event and then we store it in S3 for storage or retention. We want to make sure that we have this data even when the Kafka brokers purge the data after the given time span that the user defines. We use this for very sensitive data that we may have to replay later on for various reasons. And data will also then be sent from our Kafka clusters to other downstream tasks, which include being put into a database. So given that we have so much, since we have such a complex system, it motivates the reason for why we would want something to help us operate and manage all these moving pieces, whether it comes down to replacing a broker or making sure that the data is written to S3 correctly. The bottom line is that one person or a team of 5 people isn't going to be able to do all the monotonous tasks that would be necessary to make sure that the system stays afloat. So our solution to this is the Kafka Control Plane, which, like I said earlier, is a piece of software that we wrote using Temporal to do all the operational logic for maintaining the integrity of Kafka at Stripe. So what does our control plane do? We have a ton of different workflows that we've included. Some make sense to use Temporal. Maybe some other ones don't really fit durable execution. But just to name a couple of them, we have our Kafka Planner workflow, like I said, that ensures the integrity of all of our Kafka clusters at Stripe. It runs on a 15-minute cadence, and it basically just makes sure that everything is operating as normal. We have a replace broker workflow, which we use for replacing brokers in all of our clusters. We have a rebalance Kafka cluster workflow, which we use for rebalancing our various clusters. Essentially, when the Kafka planner workflow acknowledges that there's too much data on one of the brokers in the cluster, it'll execute this workflow. We have a rolling restart workflow, which we use for restarting an entire Kafka cluster. Basically, the workflow will take a broker, restart Kafka on it, then it will wait 10 minutes to make sure that everything is functioning correctly, and then it'll move to the next broker in the cluster and continue to go until everything has been restarted. We have a topic differ workflow, which I actually personally worked on, and what this does is this basically makes sure that all the configuration changes that users have to their topics at Stripe, and make sure that these configuration changes are applied. So it will do things like create topics, repartition them, cut retention, increase retention, etc. We also have the archive monitor workflow, which I talked about, which makes sure that all the data that we write to a specific Kafka topic gets written to S3. Oh, and what I'm going to do is I'm going to talk about 3 of these in more depth. I'll briefly talk about the Kafka planner one, but I'll dive a lot deeper into the replace broker workflow and the archive monitor workflow. So to start off, I'm going to talk about the archive monitor workflow. Just talking with my team, we believe that this is a good workflow and a motivating example for when to use temporal and durable execution, just because it's a very long workflow. It technically runs indefinitely, and it requires state changes. Like, it needs to remember specific inputs that are being passed into different child workflows that are spawned off. So let's talk briefly about the Kafka archiver. This is the tool that we use to make sure that all the data from our Kafka topics is successfully written to S3 buckets. So like you'd expect, users will write data to Kafka clusters, and then on a 15-minute cadence, we have an Airflow job that runs, and it takes all the data within that's been written to that topic in that 15-minute interval. It does it per partition, per topic, per partition in each cluster, and then it takes all that data and then it writes it to an S3 bucket. And like I said, people want to have this data pretty much just for a rainy day. I guess we've had users contact us and asking us to replay events given when there's like an incident or something like that in a downstream task. But yeah, I think that you get the idea of what this does. So what is the archive monitor workflow? Given that we're dealing with like really, really sensitive data, it's really important that this information that's been sent to the Kafka topics is successfully written to S3. So we use this archive monitor workflow to make sure that this data is written successfully. Prior to this workflow, we just had like a checker script that would run on a continuous basis on like a cron. And it was all right. It kind of got the job done, but ultimately what would happen is that there would be issues where the checker wouldn't be able to wait for specific S3 paths to be created, and then ultimately when the S3 pass wasn't created when the script was running, it would end up alerting the team, and this kind of became a nuisance. We were getting way too many pages per week for something that could be solved with something like a workflow. So what this is it's a workflow that's comprised of both a parent and a child workflow. Like I said, it runs indefinitely. Pretty much you will just go into a box in one of our 4 regions. You'll then execute the workflow, and it will run until, hopefully forever, but until there's an issue. And yeah, this thing will check to make sure that the topic events are written to S3. So now I'm going to walk through more in depth about how this workflow works. So like I said, there's a parent workflow, and one of the members of my team would end up just executing this workflow at the start. Once this workflow was executed, the parent workflow, which we call the archive monitor workflow, it would spawn it would asynchronously spawn a child workflow, which we call the archive check workflow, and it would abandon the workflow. So yeah, I mean, it just starts it, and then it continues, the parent workflow returns to that scope and it continues to run. Since this archiver that I talked about runs on a 15-minute cadence, the parent workflow would then go to sleep for 15 minutes, and its job is essentially to continue to run this process indefinitely. The state that needs to be held is we need to have the timestamp, the starting interval timestamp for when the archiver actually ran, being past the child workflow. So it's important to when there's like specific things like deploys happening, to make sure that we can maintain that state and pass it to the child workflows when they're spawned. What the child workflow does is it actually does all the heavy lifting. It will, by basically just checking to make sure that all the paths are written to S3. Some of the operations that it does is it first has to start by generating all the paths. And this sounds like pretty simple, but given that we're managing like thousands of topics across tons of clusters, this actually, well, the generation part is pretty simple actually, my bad. It does it pretty quickly, but the thing that takes a really long time is checking on the cluster to make sure that every single path exists. And it does so by just checking the hash of the generated path exists on that specific cluster, or on the specific broker. This was, we think that this is like a really good motivating example for why to use Temporal, because in that child workflow, there's an await statement that will go and and wait for all of the paths to first be generated and then also to be checked. Previously in the script, it didn't do so exactly, and yeah, like I said, we got a lot of pages, but by using this workflow, we were able to mitigate a bunch of this spurious nonsense that would bug our runner. But so as this child workflow is running, this check workflow runs, it will continue to run until there's an error, and when an issue happens, it will terminate, and it will notify us through PagerDuty that the workflow isn't working, which is useful given that we're dealing with payment data. The next workflow that I'd like to talk about is the replace broker workflow. This, I believe, is our best motivating reason, or best motivating example of when to use Temporal. And just as you'd think, it replaces the brokers. It's used to replace brokers in Kafka clusters. So when do we replace a broker at Stripe? There are two specific instances when we want to replace a broker. The first is going to be when it's unhealthy. We will just call the AWS API, and that will notify us whether a specific instance is unhealthy. When that's the case, we'll spawn this workflow to run it. The other time is going to be when the workflow has run out of, or has come to completion of its host lifecycle time span. So one thing that what we have to do across all infra at Stripe is that whenever we want to replace our brokers or our instances on a 28-day cadence. So pretty much whenever that time frame is done, we go ahead and replace the broker. So the original implementation was pretty simple. What we would do is we would first detect that there was an unhealthy broker. We would make a call to terminate the ASG through the AWS API. And then after that, we would wait for the instance. We would wait for AWS to spin up a new instance of the broker. This seems all well and good. However, we ran into an issue where when spinning up a new broker takes a lot of time because we have to wait for it to completely bootstrap and before it can be actually promoted to be within the cluster. And this operation, waiting for it to spin up, would take a total of 20 to 30 minutes, which is kind of scary given that we are very concerned about having high availability throughout our entire platform. And during this 20 to 30 minute times, we would have under-replicated partitions. it gets even more worrisome given that potentially there could be more brokers that go down during this time, which could lead to eventually offline partitions, which would just be not being able to access data on these brokers. So we came up with a different implementation to reduce the time in which we had this under-replicated partition state for our brokers. And so the way that we did it was originally all we had was a Kafka cluster. Like I said, we would just replace the brokers through AWS. But what we introduced is we added for extremely critical clusters that actually are within the charge path or that have a lot of payment volume going through them, we added a couple of standby brokers. And the idea here is that we would want to take these standby brokers and then promote them to within the cluster to basically whenever there was a broker replacement happened. So let's talk a little bit about how the setup of our broker works to understand how this workflow is what this workflow is going to do. So as you know, we have like an instance that is the broker, and then within the broker, we would also have three EBS disks attached to it. We have one that holds the operating system, one that we use to store all the open source software to run the broker, and then one that we would use to store all the Kafka data. The idea behind this workflow is that we'd want to take this EBS disk with the Kafka data. Well, there'd be two EBS disks with Kafka data, one on the active broker in the cluster, and then one on the standby broker. And we would want to swap the place of the active and standby broker, and then do a hot swap with the EBS disks. So let's see how that would work. So just to give like a frame of reference, this is our setup. We have our active broker and our standby broker. What we would then do is whenever we have to do a replacement, we would start by unmounting and detaching the EBS disk from the standby broker. So we would unmount and detach the EBS disk from the standby broker. The next thing that we would do is we would turn off the Kafka process on the active broker and then do the same thing where we unmount and detach it. And then we would take this EBS disk that has all of the pertinent Kafka data, and we would attach it to the standby broker. Once this was done, we would start the Kafka process on the standby broker, and we would promote it to within the cluster. We had really good results with this. What we found is that we were able to reduce the downtime or the amount of time for under-replicated partitions to about 1.5 minutes, which is, in other words, is a reduction of 90% downtime for of URP whenever we replace a broker. So yeah, pretty outstanding results. So the next question becomes, okay, so yeah, we have this workflow that we have in place that we can use for replacing brokers, but the question then is, how can we automate this process? Because as you can imagine, with hundreds of brokers, we don't want to actually be doing this manually every single time. So what we do is we use the Kafka Planner workflow. So what does this workflow do? Well, this workflow, it runs on a 15-minute cadence, and its job is essentially to just monitor the system and then determine whether another child workflow needs to be run to correct some sort of issue. So for example, like I said, it will replace unhealthy brokers. It will replace brokers that have exceeded their timeline for compliance, and it will also rebalance clusters. So there are some issues with this. As you can imagine, if you're replacing tons of brokers within one cluster at once, this could be a serious issue for Kafka, especially when we want to be highly available. So what we did was we came up with another piece of software called the safety barrier, which we use for adding friction in between or when these operations or state changes are done to the system. So what is this so-called safety barrier? Well, it's a piece of code. It's essentially just a class that we wrote that will that you can use to encapsulate any block of code or any workflow in this case. So you can just take your workflow, throw it in, and then there will be friction applied. And the idea is that whenever you call the safety barrier within your workflow, it will create a JIRA ticket that will require someone to go and approve the operation that's happening. And in order for it to continue to run. And we use this for rolling out new features to the control plane. So for example, when we first enabled rebalances in the control plane, we used the safety barrier to basically make sure that everything was running correctly, or whenever a rebalance needs to happen, we would go and check to make sure that everything in the system it looks fine. For example, we wanted to make sure that maybe not that much data is being sent to the cluster, to the specific cluster that's being rebalanced, because a rebalance could saturate the network bandwidth and cause issues. So yeah, that's one thing that we do. We use it to roll out new features. And another thing that we do is we use it for adding additional friction to potentially dangerous state changes, for example, like replacing brokers. Another one that we use the safety barrier for is ensuring that there's no data loss when we apply specific configuration changes to topics. So for example, when it comes to reducing retention, we make sure that one of my team members has to approve the safety barrier before making that retention cut. So let's walk through how exactly this safety barrier works. First, the Kafka planner or some person will spawn a workflow. It will then create the JIRA ticket, and then that user or some person on the team, after they're notified, will either get to cancel the workflow and terminate it, or approve it and it will run as expected. Another nifty feature that we have with the safety barrier is that we have it as a feature flag. We can turn this on and off. So for example, when I just came off on call a week ago, there were times where some of our brokers weren't being replaced successfully because of an AWS error. We can turn off all of host lifecycle management very easily by just turning off a feature flag. So some of our key takeaways from building the control plane. I think one thing that we really like is the state machine, like I've kind of alluded to before. So for workflows like replacing brokers and the archive monitor, it is really helpful to be able to have something that can hold state. Like if you think about the replace broker workflow, there are tons of different operations or tons of different steps that need to be done one after another in that specific order in order for it to work. Like for example, we wouldn't want the EBS disk from the active broker to be attached to that standby broker before we were able to verify that the EBS disk from the standby broker was correctly detached. It also helps, for example, when deploys are happening. If there's a deploy that happens, then we wouldn't have to restart the workflow from scratch whenever a code change occurs, which is really helpful, especially given that these operations can be time sensitive and can take a while. Kind of like building off of what I said earlier, activity retries are helpful for these workflows. It's good to be able to have something that will automatically retry one of these activities, like I said, like for detaching an EBS disk, for example. Yeah, these are some of the things that we like about the state machine aspect of Temporal, and why these are good examples for those workflows. I guess another question that you could ask is, why would you want to use Temporal versus a Kubernetes operator? I think that our team really likes the fact that it's really easy to write code that to write code that encapsulates like all this durable execution, and it makes it really easy to configure. I think that most of the Kubernetes operators out there that are used for managing Kafka are more of a declarative approach. They expect you to, or you tell the operator, hey, we want this specific state change to happen, but it doesn't really care about how it gets there. And given that we have very specific setups to Stripe, it's nice to be able to write more of an imperative operator that can write very fine-grained activities that happen before or for that specific state change to occur. And another thing is that our system isn't entirely built on Kubernetes, and so it is helpful or it's useful to have something that's more flexible like Temporal for building out this control plane. Some of our other takeaways, I think since we aren't really like we aren't the workflow engine team, we weren't we weren't experts in the technology when we started to build, and we made a lot of mistakes along the way. I think the first thing is when you're a novice to Temporal, just know that there's a lot of configurations that you have to set up when you're writing these workflows. One pretty big mistake that we made was we didn't actually define our activity heartbeating, and so we set like, hey, we'll set this activity heartbeat timeout, and all of a sudden we just had all these activities failing and these workflows failing, and we were like, what's going on? We look at the error message and it's like activity heartbeat timeout. We were just banging our heads against the wall for a while until we realized, hey, we never actually implemented the activity heartbeating, which is pretty bad. But yeah, there's a lot of configuration that you have to set up when writing workflows, which is kind of a learning curve. I think that I kind of spoke to this earlier, but we made some poor design decisions when building the control plane. Our current implementation is pretty primitive. We only use like parent workflows, child workflows, and activities. We don't use like any other offerings that Temporal has. And I think that we also included some workflows in our control plane that didn't really make sense or didn't really necessarily need to be there. For example, like the Kafka planner workflow, like there's no reason why that should be a workflow. I think that could work as a cron and then call some API, and it would be a lot easier and make a lot more sense. Same thing with managing topic configurations. There's no need for that to be incorporated in a workflow. Another thing that was that kind of made us make some weird kind of code design decisions was that there is a limit on like the amount of data that you can return from each activity. This was very, very relevant when designing like the topic differ workflow, specifically because part of the workflow goes and pulls all the topic configurations for that specific cluster. And since we couldn't take that configuration, the entire JSON of configurations and pass it between activities, what happened was that we would have to call the method or the API that would return this information in every single activity, which is kind of, it works, but it's just kind of weird. But yeah, I think that if we were to go back and redesign this control plane, we would come out with a very different product. But yeah, that's all I have to say. So thank you for coming to watch or listen.